Welcome. This is my AI jacket, so I'm so protected from all the blizzards that come with being in AI. We are software developers. We're very excited to be introducing to you this very soft introduction into the paper that introduced machine learning, basically large language models to the outer public, to the general populace. It's called Attention is All You Need. It's a very detailed, very advanced, very complex paper, but however, we're going to try to just simply introduce you to it in a very, 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 very simplified way so that you first understand it conceptually and then you start getting into the details. So that's the whole attitude of this site, this channel. We are all about introducing this exciting world of AI to non-believers or to people that have never heard of it before. Even developers who are in other fields that would like to start getting into AI. So you're welcome. Enjoy it. Please feel free to stop it at any time and repeat and roll forward and rewind until you understand what the concept is. It's all about AI. Thank you. Have a good one. We are just going to cover Attention is All You Need, the foundational paper on large language models. So we're going to simplify it to such a degree that it will be like kindergarten level, so that at least you can gather the basic premise of it, what is happening behind. As you see on your screen, we've got the document, the paper for Attention is All You Need, which basically is the one that gave birth to this level of large language models. And if you look at the diagram, basically you have any input which can be a sequence of characters. Let's call them sentences. Let's call it a sentence actually. And then if it's a particular sentence, like the man kicked the boy, you then encode each word. Basically that takes two steps. The first step is to encode the word. Each word in the English language, you give it an alphabetic identity so that any word, John, Peter, Mike, I am, and so forth, each word has got a unique ID in the English language. So that's the first thing. Each word is a unique identity, but also each word is a position in a sentence, and you also encode that so that you've got two positions. The encoding of the word is a number, and then its position within the sentence as an additional number. And that's basically the positional encoding. As I said, we are simplifying at the moment. The positional encoding is actually done through an equation that involves sine and cosine, but for now, let's just call it a unique number that represents the positional encoding in the sentence. And then we are going to do single head attention, which I'm going to explain in the next few next few slides. That's as far as we'll go in this particular video. Basically, this box here is what we're just going to cover in this video, from the way up to here, up to this first box. And that's basically the encoder. We'll cover it in a simplified form, but we'll also then cover it in a further detailed form. In fact, we'll keep abstracting deeper and deeper into the detail until we're actually covering the equations. But this is a very entry level video, so please, if you have advanced understanding, you can skip the video. But if you are starting out and you're new to this topic, this is going to be something that you're going to enjoy. Thank you. With large language models, unlike recurrent neural networks, the position of a word is part of its meaning. It contributes to the semantic meaning of the word. And therefore, if you have a sentence like you see there, the man kicked the boy or the boy kicked the man, in large language models, it is taken account of, or it is accommodated, because the index of the word, each word like man, each word has got a unique index in the language. Let's say English, it's got a unique index, a number that uniquely identifies it, and is part of its meaning and is included in the encoding. Then the second thing is its position in a sentence is also part of its meaning and is encoded as part of its semantic meaning. And so therefore that is what has revolutionized large language models. And if you look at the bottom of the slide where you've got associations, that's now the attention element of it, meaning besides the positional encoding and the uniqueness of the word, its identity, its association with other words in a sentence is also encoded. In other words, if you look at the word da, it has got a meaning to the words man and boy, because da boy, da man, it means da is associated very much with the word that it is addressing. And if you look at the word man, it is associated with what it is kicking, which is the boy, but also with the action that it's taking, which is kicked. So it's got a secondary and a primary meaning, or association or attention. If you look at the word kicked, similarly, kicked is directed at the word boy because that's where the action is directed, but it's also in a secondary sense associated with the addresser of that word, the determiner of that word, which is da. So basically that's how large language models are differing from the old recurrent neural networks, because the position of the word affects the meaning and is encoded as part of the semantic sense of the word, and as well as the association is of each word vis-a-vis any other word in the sentence is also included as part of the semantic meaning. Thank you. This is the encoder. What are we doing? We are predicting one word at a time. Predicting one word at a time. So when we start at the very beginning, the sentence that we have is the man kicked the boy. But at the very beginning, we only have the word da. That's the first word. So because we only have the word da, it then calculates against itself. So the first calculation is da against da. And because we know the answer, because we are training, we know the answer of da and da should be men. If we calculate this equation here, query times weight, key times weight, where weight is random numbers, which are basically these numbers here, which are random numbers, which are the x. We'll get the answer. We know the value because we know the value for da and da should be men because that's the next word. Therefore, we'll be able to know what the weights are. And then once we know what the weights are, we save them and we go to the next word. So it's happening one word at a time. So the first time the query runs, da and da will give us men. The next time da men will give us kicked. The next time men kicked will give us there, and so forth and so forth. So that's what's happening in real time. If we now say, okay, so how do you get the query? What is the query times weight? What's the Q? What's the query? The query is basically each word has got a semantic meaning. So you take its properties and you build a table of values. So if you say the word da, is it a word? What word type is it? Is it a noun? Is it an adjective? You put a number there that represents the word type. Is it a stop word? Is it does it associate with gender? Does it associate with age? What's its attention from this table? And what is the word code? What is the unique identifier for that number in the alphabet? For that word, in the alphabet, like the word da, you put that number, and then the same thing with the positional encoding, its position in the sentence, what word represents its position. That word is actually a sine or cosine function, but you can even just simplify it into a word like 0, 1, or 2, or 3, or 4, or 5 on a sentence, right? In a sentence. So once you have these two tables where one is the query, one is the key, right? You then convert them or normalize them, min-max normalization, into numbers, and all the numbers should add up to 1 for a particular column, so that each number represents the relative value of that number vis-a-vis the relationship to the full value 1. So that's so you then have a matrix like this. Then this matrix or matrix, whatever, you then multiply it against another matrix, which is the weight. And this matrix here is random at first. We just put random values. But once we do this calculation and get the value, because we also know the value, we'll use the same system, same function, same, matrix, and, accept it, then we know that value. And once we know that once you act against that value, it means we then know the weight. Like I said, 5 plus x is equal to 5 is equal to 10 means x is 5. For that same reason, we'll be able to derive what are the weights. And once we know the weights, we save them, and that is basically encoding. That process of saving the weights is basically encoding, right? And so I hope in this first sweep that I've done, you've understood what is going on. We are encoding, predicting word by word, and we are using the matrix that is derived from the properties of each word. In the first case, the word is a query. In the second word, the word is a key. And then when the two are multiplied by random weights, it should give us the value that we know is men. And when we calculate men, also given its matrix, we know its value. And then because we know its value, we are able to then calculate what are the weights. And then once we know the weights, we save them. And you might wonder, if we calculate these weights versus these weights, query weight times key weight, we get what are called attention scores. Obviously, there will be random matrices that will come out. We then standardize those, normalize those attention scores, and then we softmax them to make sure that they are within the limits that we can relate to the final value, which is the word that we're trying to predict, which is man. So this is really the process that happens. So this is a very approach to understanding the whole process. When we do it the next time, we are going to abstract deeper into the detail and actually use the actual mathematics so that you can see how it actually works in real time. But this is supposed to give you a conceptual understanding of what is happening at the time in which you are encoding your values into a large language model using matrices, using the query key value paradigm. Thank you. That's a mouthful.